Testing on YouTube. 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 Testing, testing. Testing on YouTube. I think we're good to go on YouTube. Testing, testing. All right. Just one more. Testing on X. Testing on X. Testing on X. All right, I think this is live on X. Let's see. Nope, not yet. Almost. Almost. Testing on X. Testing, testing, testing. Some kind of keyframe error here on the stream. What is going on? Qu'est-ce qui se passe? ¿Qué pasa aquí? Is this still working? Yeah, okay, it's still working on YouTube. It's just not working on X. How's it going? Kong Huang and Sataki. All right, I think we're finally live on X here. Let's make sure. All right, there we go. Live on X, live on YouTube, and live on Twitch. We're good to go. Let's get started. All right, welcome everybody to another Hoopo stream. This is going to be a pretty nitty-gritty deep dive technical stream on some computer vision stuff. You know, I feel like we've been reading too many agent papers, kind of like high-level stuff, so I wanted to go a little deeper into the details. And we're going to be looking at 3 different papers today that are all kind of related, and I think they make us ask ourselves some interesting questions here. So the 3 papers we're going to be reading are MeshFormer, a high-quality mesh generation with 3D-guided reconstruction model. This is a paper released on the 19th of August, 2024 by UC San Diego, UCLA, and Hillbot Inc., which is some new startup, I think also San Diego-based. And this is a mesh generation paper, so they're using generative AI to generate these meshes. The next paper we're going to be looking at is also similar in that they're generating meshes, but they're doing it in a completely different way that I think is very interesting. And this paper is called MeshAnything, Artist-Created Mesh Generation with Autoregressive Transformers. This was released on the 14th of June, 2024. So a little bit older now, but like I said, it's interesting because it provides a good kind of contrast to this paper because they generate meshes in a completely different way. This paper comes out of kind of like a hodgepodge of different Chinese academic institutions here, as well as SenseTime and some Chinese computer vision companies. And finally, the last paper we're going to be looking at, and I think it kind of complements the first 2 because in a way it's almost an extension of what makes this paper unique. But this paper, which was released the 15th of August 2024, called JPEG-LM, LLMs as image generators with canonical codec representations, out of University of Washington and FAIR, Facebook AI Research. I think now it's called Fundamental AI Research or something like that, but basically Meta's research lab. So all three of these papers are about generating vision things. I don't know how to bucket that, but here you're generating images, right? Two-dimensional images and videos, which are two-dimensional images over time. So a sequence of two-dimensional images. So that's images and videos. And then here we're going to be generating meshes, which are basically a collection of vertices that represent some 3D object. And in this one, it's also meshes, but these meshes have a little extra secret sauce in them that makes them look much cleaner, obviously, because if you look at this, right, these meshes don't look anywhere near as good as these meshes, but there's some tricks that they're using here to make it look like that. So let's start with this first paper here. So this is given a sparse set of 6 multi-view RGB images and their normal maps as input. MeshFormer reconstructs a high-quality 3D textured mesh, right? So here, the word textured there means that each of these meshes, in addition to the actual vertices like this, right? And this is what I would call the mesh, but the texture is effectively a image that is wrapped around the mesh, right? So for each of these textures, you have some corresponding image, right? Like a PNG with some specific mapping that allows you to wrap it onto the actual mesh. So that's what a textured mesh is. Okay. Multi-view RGB images means that this model is going to take as input multiple RGB images, right? So you can see here that ultimately when you're creating the mesh for this bust of a bearded man, you're going to require 6 different views of the bearded man from the front, the back, the top, the different sides, and so on, right? And that multi-view input allows you to kind of understand the object, and then once you understand it, you can kind of generate the mesh. But the part here that's going to make this paper special is this idea of a normal map as an input, right? So what is a normal map? Maybe, actually, let's read this abstract, and then we'll go into what a normal map is. So again, this paper's presenting MeshFormer, right? And that name comes from the fact that it's a mesh transformer, right? So it's a transformer that creates meshes. It's a sparse view reconstruction model. So you're using multiple views of the object, and it's reconstructing the 3D object. And the sparse view means that you don't need that many of these, right? So if you needed 700 multiple views, it wouldn't be a sparse view. But the fact that you only need 6 of them, that's considered sparse. So that's where that comes from. Instead of using a triplane representation, we store features in 3D sparse voxels and combine transformers with 3D convolutions to leverage an explicit 3D structure in a projective bias. I think we'll get into that a little bit later, because I think if we open that can of worms, we're going to get a little confused here, without the need for complex multi-stage training processes. Okay, so we were going to go into what exactly is a normal map and why is that important. So if you see here, each image also has a corresponding normal map, and these images are aligned, right? It's like basically the exact pixel by pixel correspondence, right? So every single pixel in this normal map corresponds directly to the pixel in the RGB. And a normal map, let me see if I pull it up, is this, right? It's an image. It's also an image, but rather than the value at each pixel being some RG and B representing the color of the object at that specific pixel, instead, what the color is representing in a normal map is the direction of the normal vector, right? And the normal vector is the vector that is perpendicular to a surface, right? So, for example, something like this, right? You have this cone that sticks out. This is kind of what the normal map for this cone looks like, right? And people have been using normal maps in 3D pipelines for a very long time because they allow you to get a more 3D kind of effect, right? So I think this image that I had pulled up makes it the most obvious, but you can see here, this is just a standard PNG texture. And when you add the normal map, you get this kind of effect, right? And this is an illusion, right? Because ultimately when you're using these type of physically based rendering pipelines, you're actually calculating the way that the light rays intersect with the object and looking at those angles and doing all this relatively simple geometry, but kind of tedious geometry and math in order to calculate what it looks like from the point of view that you're rendering these objects and these lights in the scene, right? If you have the direction of the normal, which is the direction of the normal vector of the surface, you can better calculate the way that the light is going to bounce and the way that all of that type of stuff interacts, and you're going to get this kind of more 3D look. But again, it's not like a real, it's not like you're actually representing the object explicitly in 3D, right? You're effectively leveraging your rendering pipeline and the fact that knowing this normal vector improves the way that it's going to look to get this kind of more higher quality 3D looking effect, right? So that's a normal map. But where we can get these normal maps, right? Like, normal maps are great, but how are you going to get this normal map for some arbitrary mesh, right? And that's where the key insight of this paper comes from. And the key insight of this paper is that you can use diffusion models to generate these normal maps, right? And here I'm going to talk about this paper a little bit. This paper, I think we reviewed this one or the previous version of this one. There's been a couple of these papers now, but this is basically MeshAnything, unleashing the power of large-scale unlabeled data. And in this paper, they train a model with a huge amount of labeled images where you have the actual image, and what you want to get is this depth image, right? So you're going from a real image into this depth image. The depth image is kind of similar to a normal map in that it's basically pixel by pixel matching this real image, but in a normal map, it's telling you the direction of the surface normal, but in a depth map, it's telling you the distance of that pixel to the camera, right? And it turns out that if you have just 1.5 labeled images in this MeshAnything, but different depth estimators use different data sets, different amount of labeled images. Some of them are fully supervised. Some of them are kind of like self-supervised in some ways. So there's some differences here. But the key result from this research direction is that these models generalize very well, and that you can start taking pretty much any image and feed it into one of these models, and it'll produce a pretty good depth image. So that's useful, but you can also do the same thing with a normal map, and that's what they're doing here, right? So they're taking these multi-view images, they're feeding them through some kind of model that gets you, right, a normal map images input, which can be estimated using an existing 2D diffusion model. So you're basically doing multi-view, sparse multi-view reconstruction with additional normal maps, which allow you to get extra crispy meshes. And the reason you have those normal maps and the reason people weren't using them before is we didn't really have the ability to create normal maps from arbitrary images. But now that we have these diffusion models that have been trained to do this task specifically, right, we can use these 2D diffusion models and all the intelligence that they have in there to get normal maps. And then once we have these normal maps, then we can basically generate much higher quality meshes. How's it going, Miguel? And then how's it going, Oma? All right, so let's keep going with this paper. Here at the end of the introduction section, right, this is when there's the abstract, which is the summary of the whole paper in one paragraph. Then you have the introduction, which kind of sets the scene and kind of lets you know kind of maybe where the idea kind of came from, what other people have done. And then at the end of the introduction section, they're going to list these bullet points where they kind of describe specifically what all the different contributions of this paper are. So here are the contributions for the MeshFormer paper. So they're going to be generating high-quality 3D textured meshes with fine-grained geometric details in a few seconds, right? So their architecture allows it to be slightly faster. That's kind of one of the stories that they're trying to spin in this paper. They're going to be using 3D sparse convolution and transformers, explicitly leveraging 3D structure and projective bias, which means that this 3D sparse convolution, you're putting in a bias into this architecture for the 3D nature of this object, right? You know that you're going to be generating these 3D things. These are 3D objects. Therefore, if you put some kind of inductive bias in there that is 3D as well, then it's going to be an easier task to learn than if you didn't have this kind of explicit 3D bias. They use a unified single-stage training strategy. This is maybe one negative feedback I have with this paper. This really isn't the case, right? They keep talking about this. They mentioned this in the abstract as well, without the need for complex multi-stage training processes, but that's not the case because they're literally using a pre-trained 2D diffusion model to train to get this normal map. So they're more referring to the fact that this entire pipeline here can be trained all at once, right? It's not like you need to train this part separately from this part. But the reason I kind of disagree with their claim here is that they're using other models that have been trained for them, right? So if you wanted to actually train everything you need to generate from scratch, you would need to also train a 2D diffusion model and train this 2D encoder here. So like they're using pre-trained models, but they're pretending that they didn't have to train those pre-trained models, but they didn't. But if you wanted to do this from scratch, you would have to train those. Okay. First to introduce multi-view normal images as input. And that is really, I think, the key insight of this paper is this idea of using normal images to improve the generation. Okay. So we're going to skip through the related work section here and get to this point here. They take normal maps as input in a feed-forward reconstruction model and task the model with generating 3D consistent normal texture for geometry enhancement of sharp details, right? Once you have this normal map, right, you can go a little bit deeper. You can basically generate finer level details in geometry, right? Okay. Let's see. Most of the methods rely on a combination of a triplane representation. And then here they claim that they're not doing the triplane, but instead they're using a 3D native structure such as voxels. I feel like the triplane and the voxels are a little bit more similar than they think they are. In this paper, they make it seem like triplanes and 3D voxels are almost completely different, but really, I think they're a little bit more similar. And let me kind of justify that. So where do I have my triplane? This is a triplane. Okay. So a triplane representation is this one here. This is from a completely other unrelated paper. So voxels is whenever you take some bounded volume in space, right? So you have this 3D volume in space and you are boxing it out into these little cubes, and then each one of those little cubes is called a voxel, right? So in this paper, whenever they go here and you see these, let's zoom in here so you can see kind of the details. You see this kind of version of the bearded guy with the mesh that's made out of all these little cubes. Those are the voxels, right? And the voxels have some resolution to them, right? You can have a lot of voxels, so it's going to take a lot of memory. It's going to be longer to train, higher resolution. But you can also kind of have a lower resolution in your space, which means just less voxels, right? A triplane representation is, in my opinion, very similar, right? Rather than having kind of voxels everywhere in this 3D space, you instead have 3 planes, right? And the plane is just this 2D flat kind of infinite plane, and you have 3 of them that are orthogonal to each other, creating this triplane, right? And you can encode information on each plane separately, and then when you want some feature associated with some specific point in 3D space, you can simply look at the corresponding points on each of the planes, concatenate them together, and then that'll give you a feature for that specific point in space, right? And that's why I feel like, to me, there's not that much of a difference between a triplane and voxels, right? Like ultimately, triplanes are also a type of 3D inductive bias. So I don't know. Triplane representations often show results with noticeable artifacts at the boundaries of patches. So here what they're referring to is that whenever you have these triplane representations, right, there's one feature for this, and then there's one feature for this, and then there's one feature for this. So at the boundary of these, whatever the discretization level you use for your plane, right, you're going to have suddenly the features suddenly change as soon as you cross that boundary, right? So there's going to be some discontinuities in the feature representations for each point in space, depending on whether or not they're crossing these boundaries, which are effectively how discretized you're doing each of the little blocks. But that also happens in voxels, right? So here they're kind of pretending that voxels don't have that same exact issue, right? Like there's also that case in voxels. In voxels, you're also going to have this discretization, where you're breaking it up into these little voxels. And as you go from one little voxel to the next little voxel, you're also going to have that issue where you might have these kind of boundary situations where suddenly the feature that represents that voxel is slightly different from the feature that represents this voxel. And whenever you're using that to condition some kind of model, you might end up with slightly different outputs for 2 points that are very, very close together just because they're separated and they're in different voxels. So, okay, that's triplanes and that's voxels. This is a kind of a complicated looking thing, but really it's a little bit less scary than you think it is, right? So this whole part down here is really just a U-net, right? So here they say a 3D U-net architecture while integrating a transformer at the bottleneck, right? So this is the U-net. The U-net, you could think of it like it goes from high to low to high, right? It goes up, down, up, right? And the up, down, up is basically in the resolution, right? So you can see that at the beginning of the U-net, of the 3D U-net, you have a high resolution of a large amount of voxels. And then as you go down and down and down into the bottleneck, this middle part is called the bottleneck of the U-net. You're decreasing the resolution, but you're also increasing the dimension of the feature space, right? So here it's kind of small features for a lot of voxels, and here it's like a very long feature for a very small for a larger voxel. In the middle, you have this bottleneck. The bottleneck, you're going to basically just shove a transformer in there. So you have the kind of standard parts of the transformer. You have the self-attention block, right? And then you have the MLP block. So this is kind of the standard parts of the transformer blocks. And then the other side of the U-net, you go back up, right? So that's the U-net right there. What else here? Iteratively performing projection-aware cross-attention and 3D sparse convolution, we could compress the 3D volume to a lower resolution one. So in every point in this U-net, you're performing this projection-aware cross-attention. Projection-aware cross-attention basically means that it's some kind of attention mechanism, right? That is not self-attention, where you're just performing attention with itself. You're doing cross-attention, so you're attending two slightly different things. And in this case, what are you doing the cross-attention with? You're doing it with the RGB patch versus the normal patch. So basically, the features coming out of this RGB image and the features coming out of the normal image, right? So you're taking a little bit of the information coming out of the normal image, a little bit of the information coming out of the RGB image for each individual little part of it. And the projection-aware is saying that basically you know where, what projection or what view this is coming from, right? So you kind of are aware of, like, are you looking at the front of this or the back of this or the top of this, right? So that's basically what it means by projection aware. Okay. This 2D encoder here, I think they mention it, but it's basically a dyno. I think they mention it down here. Maybe not. I thought they mentioned it somewhere. Okay. I need to get better at highlighting, but this encoder here is pre-trained. And then they also have the diffusion model that generates these normal maps is pre-trained. So those are two different pre-trained models that they're using, right? So what they're training from scratch is this U-net here. And they're also training this these three little multi-layer perceptrons here, right? So they have three little multi-layer perceptrons. One of them is estimating the normals, one of them is estimating the color, and the other one is estimating the SDF. SDF is the signed distance function. So I also have a image for that so that you guys can understand what a signed distance function is. This is a famous rabbit, right? This rabbit has appeared in computer vision papers for a very long time. Here you have the surface of this rabbit. Here you have the rabbit inside a bounded volume, right? The bounded just means there's boundaries to it. So there's some limit on the X, Y, and Z. And here is a signed distance function. The signed distance function is a function that tells you the distance to the surface of the object, right? So you basically know if it's right on the surface, it's going to be 0. The function is going to tell you, okay, for this point in space, the value is 0. If it's right outside the surface, it's going to be some positive value. And if it's underneath or inside the surface, it's going to be a negative value. So it's basically giving you a negative number, a positive number, or a 0, depending on whether you're on the surface, outside of the surface, or inside the surface, right? So the normal is the direction of the surface, the color is the color of the surface, and then the SDF is kind of the actual geometry of the surface, if you want to think of it that way. With an SDF and a color texture like this, you can create a mesh from that, right? And usually what people use for that is called a marching cubes algorithm. I have a nice little marching cubes algorithm. This is also kind of old school computer vision, but let's say you have some surface, right, which is maybe defined as an SDF. You can divide your volume of space into little cubes. You start saying, okay, these points are inside, these points are outside. Let me go a little bit finer resolution, right? And you kind of march along these boundaries of your sine distance function to eventually get to a explicit representation of that surface, right? So you're going from some function which defines the surface, like an SDF, to something like this, which is just a collection of points, a set of points with some connectivity, and that is a mesh, right? So this pink line here is a mesh. This is an SDF. And marching cubes is how you can get from an SDF to a mesh. Okay. The input multi-view RGB and normal images are initially processed by a 2D feature extractor, such as a trainable Dyno V2, to generate multi-view patch features. So right here, they're feeding in this normal and this RGB image into the Dyno V2. And this is, I don't know if they mentioned this, but like Dyno V2 probably wasn't trained on a whole lot of normal map images. So like, I'm actually kind of curious that these normal maps like kind of just magically work, right? Because you're not even using the normal maps kind of explicitly. You're using the normal maps after they've been fed into a pre-trained model like Dyno V2. We project each 3D voxel into the M views to interpolate M, RGB, and normal features. So the part about this that I don't like is that one of the difficult things about these multi-view reconstruction papers is that if you're using something like this, right, like a virtual object, you can get multiple views and you know exactly what the camera position was for those views, right? So like, you know exactly where the camera is relative to the object for this, and you know exactly where the camera is relative to the object for that, right? And because you know exactly where the camera is, you can do this type of stuff here, right? Where you're basically expressing in the camera coordinate frame, you're converting them to a unified world coordinate frame, right? You can switch from frame to frame, right? You can do this type of projection aware conditioning. But that's not always the case, right? In most real-world situations, you don't have the exact camera position of each of these multiple views. So that's one thing that makes this approach maybe not usable for arbitrary multi-view images in the real world, right? It's going to be really good for simulated objects or objects where you can kind of, you know where the camera is. Okay. They project each voxel. V denotes a voxel feature. So here's your cross attention, right? Your cross attention, you're doing attention between two slightly different things here. Here you're going to be doing cross attention between the voxel feature. So each little voxel has some feature vector that kind of tells you what is in that voxel, right? Kind of the same way that a triplane works, right? Where you're kind of saying, okay, there's some feature here, some feature here, some feature here. I'm concatenate all three of those features, and now I have some feature which represents this position in space. Kind of the voxel feature is the same idea. It's like, okay, this little tiny cube right there, there's some feature vector associated with that. PIV denotes the projected 2D pixel feature. So PIV, this is what's coming out of the Dyno encoder, right? So you're feeding your RGB image into the Dyno encoder. This giving you some feature vector, and then you're saying, okay, here is the feature associated with this 2D pixel, either the normal pixel or the normal feature GIV or the RGB feature FIV, right? So they're feeding the RGB through a Dyno and the normal image through the Dyno. Okay. And that's pretty much it for that. Coarse 3D occupancy value with a binary value indicating whether it is close to the surface. So that's this occupancy volume here, right? So one of the things that makes these slow is that as soon as you go into the world of 3D space, right, having to do some amount of computation for every single point or every single voxel in 3D space can get very computationally expensive, right? Because the volume of space is increasing to this third power here as your 64, which is the length of each side, increases, right? So you can't do 256 by 3 if every single voxel requires some computation. So you need to turn this feature volume into a sparse feature volume. Sparse just means that a lot of it is empty, right? So this first step here with this occupancy volume is really just about getting rid of all the empty space, right? You don't need to be doing any kind of calculation for all the white space around this guy, right? You don't need to be like encoding for this patch here and this patch here, and then doing cross attention between the white patch and the empty space, right? You can get rid of all that computation, and that's how you can get it to be a little bit faster. So that's why they have to go use this occupancy volume to get to a sparse feature volume so that they can be a little bit more efficient in terms of compute and memory. Okay. In terms of the losses, it's kind of a complicated combination of different losses here. So you see they are using the marching cubes in order to get the final 3D mesh, and then once they have the final 3D mesh, they can get those pictures, and then once they finally get the pictures, then they can use a kind of a standard reconstruction loss, okay, and say, okay, here's the final picture that I got at the end of my pipeline. This should match this picture here. I do some kind of loss that diffs those, and then I'm going to get some kind of gradient, and then I can basically push that gradient all the way through all this crap here, and then that's what they mean by they train this in a single stage, right? Because sometimes these techniques are a little bit complicated, and you have to train multiple different things separately, but in this case, they kind of train all of it at once, and they're pushing those losses through. So you have a couple different losses here. You have the color loss, MSE, LPIPs, normal loss, so two different normal losses, MSE and LPIPs, and then the SDF, so kind of the surface regularization here, and then the L occlusion, which is probably occlusion based on the this thing here, occupancy volume, occupancy, L occupancy rather than occlusion. That's probably the better, that's probably what they actually mean. How's it going? Sotaki Newman Bunny, and then like a little Kirby emoji. So, okay, there's a question here from Mr. Kirby emoji. I may be a lurker and VOD goblin, but your video explanations make me feel like a straight A student. You're the best. I appreciate it, man. Thanks for the love. Okay. Fine-grained geometric details. We attempt to learn, okay, so many recent works attempt to employ large-scale models to learn mappings from RGB to geometric details, right? So what they're saying is that with these papers and previous papers, and we've read a bunch of these previous papers, primarily trained using 3D data, but it's still uncertain whether the scale of 3D data is sufficient for learning such extensive priors, right? So there's a limited amount of 3D data sets, and most of these reconstruction papers are effectively all using the same data set, right? So if you actually look here, this is using the Objaverse and the ShapeNet data sets. And I think these guys also use Objaverse. I think if we Control F for Objaverse, it probably comes up. Yeah, there you go. We train MeshFormer on the Objaverse data set, right? So both of these are actually trained on effectively the same data set, right? And according to the scaling laws, right, if you're training a model that's roughly the same size on roughly the same data set, you should probably get roughly the same performance. So why are these meshes better looking than these meshes? And the reason is because you're getting a little bit more intelligence in there coming from the fact that you're using this normal diffusion model, right? This diffusion model that predicts the normal map, right? So RGB plus depth and normal is going to give you more signal and more intelligence that you can effectively put into your model compared to using explicit 3D and RGB. Right, so the addition of this depth and normal information, which you can get from these diffusion models now that have been basically trained on every single type of image, so they're very good at all different types of image, right? It's like this scene here in the inside of a house with a bunch of humans, pretty high quality, right? This is a completely different scene. This is like the outside of a city, also pretty clean, right? So it's kind of magic that you can get high quality normal maps for arbitrary RGB images. So that's a little bit of the magic that's allowing this to get a little bit more quality than if you just train this entirely from multi-view RGB from something like Objaverse. Okay. It's still uncertain whether the scale of 3D datasets is sufficient for learning such extensive priors. It's not, right? We're not quite there yet. So we either need to 10x and 100x the 3D data, or we need to start feeding in additional signal from these depth and normals. Unlike RGB images, depth normal maps explicitly encode geometric information and can provide crucial guidance for 3D reconstruction. 2D diffusion models trained on billions of natural images embed extensive priors and can be fine-tuned to predict normal maps. That's how they're getting this, right? Okay. Multi-view normal maps as input, which can be generated using recent open-world normal estimation models. They are expressed in the camera coordinate. Okay, so that's kind of what we were talking about, where they require the camera pose, which is a little bit sketch. The learned 3D normal texture can be exported with the mesh, similar to the color texture, to support various graphics rendering pipelines, right? So this is how, now that you have not just the mesh and the texture, but you also have the normal map, you can leverage the fact that most rendering pipelines, right, in your actual like game engine, can use a normal map to give you like an extra crispy looking view, right? So this looks a lot better than this, even though it's really the same exact texture and the same exact mesh. It's just that this one has the normal map. Okay. I think that's pretty much it for this. Let's go into the other papers now, because they're doing something a little bit different, and I think it's cool to contrast. Okay. So now we're on to the MeshAnything paper, artist-created mesh generation with autoregressive transformers. In this paper, they keep using this terminology here of artist-created meshes, AMs. In this one, they don't really distinguish between that, right? In this one, they're just like, oh, meshes, right? But some meshes are created by an artist, which means that there's some guy who sat there in like Blender and like literally like pulled little vertices, and like it's almost like they're modeling with clay sometimes. That's an artist-created mesh, but you can also create meshes by scanning objects, right? So for example, this table here, or maybe this building, those aren't artist-created. Those are, someone had like a drone and they flew around this building, and then they used some kind of structure for motion type of situation, some photogrammetry to actually create the mesh for this building, right? So in this one, they specifically want to create meshes that are artist-created. And why does that matter? Because artist-created meshes have good topology, and maybe I'm getting a little bit ahead of myself, but let me talk about topology here for a second. Topology mesh. Yeah. 3D mesh topology. Okay. So whenever a human is creating a mesh, right? Whenever you have an actual digital artist creating a mesh, the mesh usually has what's called good topology, right? So good topology will look like something like this, right? Where you see how there's these very nice contour lines, which allows you to create animations that are very clean, versus maybe something like this that would come out of like some kind of photogrammetry pipeline. The topology is going to be kind of all over the place, right? You're going to have like weird like artifacts like this, and it makes animation kind of a pain. It makes texturing kind of a pain, especially around the mouth area where you have to like animate stuff. So if you can create meshes that are more like artist created meshes and less like meshes that come out of photogrammetry, right? The meshes produced by these methods approximate the shape quality of those created by human artists, which we refer to as artist created meshes. And why do we want to make meshes anyways, right? And the reason we want to make meshes is because our entire 3D tech stack right now is based on meshes. The current 3D industry predominantly relies on mesh-based pipelines for their superior efficiency and controllability, while methods for producing 3D assets typically use alternative 3D representations. So most of the papers that we're reading where people are using some kind of generative AI technique that they learn from Objaverse, right? Usually what they output is either some kind of NeRF, right? Neural radiance field. It's some kind of Gaussian, maybe it's some kind of SDF, right? And they output this alternative 3D representation, but none of our game engines and none of the tools that we use for CGI, like Unreal Engine, Unity, like things like that, those don't work with NeRFs, right? In order to actually use this created object in a Unity game, right, you need to turn it into a mesh, and that's where you rely on the marching cubes. But whenever you use marching cubes, you don't have control over the topology anymore, right? You're basically just kind of relying on this hard-coded marching cubes algorithm to give you that topology. So there still is kind of a disconnect here where all these techniques that we're coming up with, they create very nice nerfs, but then once you turn them into a mesh, they kind of look like shit, and now you're trying to use this mesh which looks like shit inside your Unity game, and it's just not that great. So if we could create a mesh that has the good topology like human created meshes, then we can just use those directly in the game without having to remesh or retopologize or like kind of do any kind of stuff on top of that. Applying remeshing to the marching cube results with different voxel sizes. So here they're saying, okay, one way you could fix the mesh that comes out of a marching cube algorithm, which you are applying on some other 3D representation, is you can do this remeshing, but even that remeshing fails to capture sharp edges and flat surfaces. And here they're kind of showing you that their technique, the MeshAnything here, right? Not only does it have way less vertices and whatever, but the topology is better, right? So you can actually see here, remeshing a marching cubes result, you're still not getting the quality that you can get from this, from a human, or in this case, a model that kind of creates that. Okay. 87GN199, depth on images comes from lens focus. No, so these, normally you can't take an image like this with a normal RGB camera and get a depth image like that, right? In order to get a corresponding depth image, usually you have to use some additional technology like structured light or like a LiDAR, right? Some kind of, there's lots of different ways of doing this, but something that actually goes and looks at the actual physical thing, right? Something like structured light, which is kind of how a Connect or an Intel RealSense works, is they project light and then you look at how that light is deformed and then you can use that to get the depth, right? There is no, whenever this guy took the picture here of this family eating this dinner, like there is no depth information there, right? What the reason you're capable of getting these depth images for these RGB images is because you trained a diffusion model that is conditioned on this RGB image and generates the depth image, right? And the diffusion model, you train it with enough different images that actually have a ground truth depth, right? An actual image where you just happen to be using a structured light camera, so you have the corresponding real image and the depth image. You train on those, and then it generalizes to new RGB images, right? So that's how you're actually getting the depth. The depth, in this case, doesn't really have to do with the lens focus. It's more explicit depth coming from the fact that these diffusion models are generalizing outside of the images that they've been trained on. But this isn't actually the real depth, right? This is just coming out of a model. Like, this is not the ground truth depth. Okay, let's go back here. These artists created meshes from Objaverse and ShapeNet. They do something pretty cool here. So they do a kind of like a data augmentation. So we intentionally corrupt the shape quality of the artist meshes and then sample point clouds from this coarse mesh to narrow the domain gap in shape conditions between inference and training. So one kind of cool thing that they do here is that whenever you're creating these meshes, right, and you want to be particularly good about the topology of the mesh, right, you can, there's an easy form of like data augmentation here where you can basically corrupt the mesh, right? So you can reorder the way that these points are kind of organized, and then in that way, create a easier kind of basin for your model to end up in. I don't know how else to describe that, right? But you're basically, because this model directly kind of outputs the mesh, if you have this ability to say, okay, well, here's the, what am I trying to say? I feel like there's no way to say this without sounding confusing. Let me come back to that. Because I think we need to talk about specifically how this outputs the meshes. Okay, we use a VQ VAE to learn a mesh vocabulary and train a decoder-only transformer on this vocabulary for mesh generation. What is a VQ VAE? A VQ VAE is a vector quantized variational autoencoder, and I think they have a definition here which paints it in a nice explanation. So here we're kind of peeking a little bit into this meta paper here, the JPEG-LM, because they have a nice description here of VQ VAEs. VQ, vector quantization, operates as a two-stage process, tokenizer training and language model training. It discretizes continuous images into these this vocabulary, right? And I actually have the picture from the original VQ VAE paper. See if I can find it right here. Right here. Nope. Right here. All right, here we go. So you have an encoder here. The encoder is taking in an image and it's encoding it into some vector that represents that image, right? So this is some kind of high dimensional vector that represents this image. And then a decoder is taking that high dimensional vector that represents that image and turning it back into the image, right? And then you can have a very simple reconstruction loss that says, okay, this image here should be the same as this image here. So when you encode the image and compress it, and then you take the image and decode it, so uncompress it, back into the image space, these two images should be the same. And this is very convenient because your kind of target is effectively what you fed in at the beginning, which means that you don't need to label any of this shit. You can just feed giant databases of arbitrary images into this VQ VAE, and over time, you'll build this vocabulary or dictionary of tokens that represent effectively the content of these images. So in this case, they're going to be doing something similar, but for 3D things, right? So let's go back here. So you have your encoder E, which projects an image X into spatial features E of X. So that's what's going on here, right? You're taking your image, you're encoding it into this image features here. The variables are a little bit different, but I think it's more about the high-level stuff here. Then each feature, it is quantized to Z by looking up the nearest neighbor in a learned codebook. So the learned codebook is effectively kind of like your vocabulary, right? The same way that when you have a language model, you have some limited set of tokens, right? You have like maybe 50,000 possible tokens, and every single paragraph of text that you can produce is composed of all of the little individual tokens that are available to you in that vocabulary. This is kind of the same idea, right? You have this kind of code book of all the possible little tokens that you could use to describe this image. And if you wanted that to be continuous, right, you would have an infinite vocabulary, right? But you want it to be a limited vocabulary, right? You only want K possible tokens. So what you're really doing when you're training this VQ VAE is you're kind of projecting this image. It's going to be some arbitrary point. Then you're going to say, okay, what this little point right here, how close is it to all the other words in my vocabulary? And I can say, okay, well, it's closest to this word right here, or this token, or this kind of visual concept right here. And therefore, I'm going to move it a little bit closer to that and then change this, right? So like ultimately what you really want to get is this vocabulary here. That's really what you want, right? By looking up the nearest neighbor in the learned codebook, anytime you see this quantizing, right, you're kind of like losing information, right? You're going from something that's infinite resolution in continuous space to something that's kind of like one of X possible options, right? It's discretized. And then your decoder G goes back into the image space, or in this case, it goes back into the mesh space. You have your reconstruction loss, codebook loss, commitment loss, blah, 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 blah. Okay, I think that's it for the VQ VAE, but now let's go back to the mesh paper where they're using this, right? So they're training a VQ VAE to learn a mesh vocabulary, right? So in this thing here, right, they're learning a vocabulary of kind of image concepts, right? So here you're encoding an image, and then you're basically, these are two-dimensional image vocabulary, right? If you want to think of it that way. But in this one, what they're creating is a three-dimensional mesh vocabulary, right? And they call this the shape, right? So they train this VQ VAE to learn this kind of shape or mesh vocabulary, and then they train a decoder-only transformer on this vocabulary for mesh generation. We treat the mesh tokens obtained from the trained VQ VAE as the language tokens in LLMs and use a pre-trained encoder to encode the point clouds into shape features, which is then later projected into the mesh token space. Okay, so what they're doing is that rather than this, right, where you basically you have this transformer, and you're feeding it into this transformer, and ultimately the transformer is just creating these features, and then those features are being consumed by these little multi-layer perceptrons here, and then you can evaluate those little multi-layer perceptrons at some volume in space, and then you can eventually get the surface, and then once you get the SDF, then you can use marching cubes to get the mesh. Like, there's a lot of little steps there. And these guys are asking themselves the question, can we just directly generate tokens with an LLM? And now we just need to figure out, okay, what tokens do we need to generate? Okay, well, let's generate the tokens that are part of this mesh vocabulary from this VQ VAE. So they train a VQ VAE on Objaverse. That gives them this code book of like shapey, meshy kind of tokens. And then their LLM is just outputting these kind of shapey, meshy tokens. And then you're just kind of like stringing them together. So it's literally like kind of building, I think, let's go to the actual page because they have like I think they have a nice little GIF that shows you how it kind of gets built piece by piece. Yeah, so you can see here. Let's zoom in here. Right, so you see how it's literally building it. It's building the mesh piece by piece. Right, which is completely different from what they're doing here. Here, they're getting this other 3D representation of the object, like an SDF or a NERF or a Gaussian splat, and then they're using marching cubes to get the mesh. Versus in this paper, they're actually generating the mesh kind of blurb by blurb, token by token, which is pretty cool. And it seems to work very well, right? And you can get higher quality topology from that, right? And because you're generating it kind of not vertex by vertex, because you're generating it kind of token by token, but because you're kind of generating it vertex by vertex, you can add noise in, right? Scramble the positions. And then because you know kind of the unscrambled version of that, it's a natural way of kind of like augmenting your data set by saying, okay, here's the final good topology, and then here's a bunch of other nearby topologies where I just kind of added noise and flipped one of the vertices with the other one, and I know what the good topology is. So then your model, not only does it generate kind of mesh token by mesh token, but it's also, because of this data augmentation technique that you're putting in there, it understands topology much, much better, right? So this model, this little transformer that they train to generate these meshes, it actually understands what good topology and bad topology is, compared to something like this, where you're relying on the marching cubes to just kind of give you the topology, and you have effectively no control over the final topology because it's just kind of whatever comes out of this marching cubes, right? So very clever idea there. These methods do not directly generate meshes, but produce 3D assets and other representations. These assets often need to be converted into meshes using mesh extraction methods. That's what we're talking about with this. And they primarily focus on the generation of shape and color while ignoring the topology of the mesh, resulting in dense meshes, right, which is exactly what's happening here. Consequently, they face challenges when applied to the 3D industry due to their inefficient topology, right? Now, the counter argument to that is that, okay, all the 3D tools we have now rely on topology, because if you wanted to animate this face, you actually have to get a 3D animator to literally animate this face by hand. But what if we start moving into a world where you're not actually doing any animation explicitly, right? So if you don't have to do any animation explicitly, then maybe you don't even need the mesh format anyways, right? If we're going to move into a world where the Unities and the Unreal engines of the future, they're not even doing anything with meshes, they're doing everything with NERFs and Gaussian splats, then you don't really give a shit about the topology, right? Because a Gaussian splat doesn't even have topology. It's an unordered set of Gaussians. So topology is really only important if you're doing things with meshes. So the reason I like this paper is because it makes me think, right? Because up until now, I was very much a NERF and Gaussian splat believer, right? My kind of worldview is that, okay, meshes are effectively going to disappear, right? Over time, we're going to get rid of meshes as a standard 3D representation format, and we're going to move to these different representation formats that seem just way better for deep learning, like SDFs, NERFs, and Gaussian splats. But this paper is making me rethink that position, because now I'm thinking, okay, well, it's going to be so difficult to refactor and change all of our 3D tools to use something like Gaussian splats. It might actually be way easier to figure out a way to just generate high quality meshes. And if we can generate high quality meshes, then we don't need to change anything. You know, we can continue to use Unreal Engine. We can continue to use lighting that is based on ray bouncing and all that stuff. So maybe this is actually what the future looks like. Maybe meshes are going to continue to stay, and they're going to continue to be the standard 3D representation, just because we have so much momentum accumulated in this direction with meshes, and it's so annoying to refactor all of our stuff and build everything up from scratch based on Gaussian splats, that maybe we just kind of end up generating meshes, and then Gaussian splats and nerfs just end up being like an oddity, right? They're just kind of like a cool little thing that people did for a couple years in the early 2020s, but nowadays everything is meshes. Something to think about. They already had point clouds to mesh used for tool scanners to make 3D models. Yeah, you can go, there's literally decades worth of research in going between all the different types of 3D representations, going from multi-view images to meshes, going from distance functions to meshes, going from point clouds to meshes, going from distance functions to point clouds, right? There's like a billion different ways to go between those, but the thing is, all of those are effectively kind of hard-coded, right? Really, you want something that's learned, some kind of learned model to go between those. And in this case, you're using a transformer that directly outputs these VQ, VAE vocabulary tokens, which are kind of like a shape token, is I think what they call it in this paper. Okay. Pipeline overview. We sample point clouds from given 3D assets, encode them into features, and inject them into the decoder-only transformer to achieve shape-conditional mesh generation. Okay, so rather than multi-view images, you start from a point cloud. Right, a point cloud can come from something like LiDAR scanning, right? So you have some handheld LiDAR scanner, you walk around the object, you get a point cloud. You could also get a point cloud from your cell phone, right? You can basically just take a bunch of pictures with your cell phone and then use a structure from motion, something like Colmap, to get you a point cloud, right? Once you have that point cloud, then you're going to use this VQ-VAE that they trained to turn that into a sequence of these shape tokens, right? And then once you have that sequence of shape tokens, you can just use transformer. I don't know if they pre-train. It'd be pretty cool if they pre-train. It's like a pre-trained transformer. But, you know, because pre-trained transformers, even though they're trained on text, they can still generalize outside of that, which is kind of a crazy concept to even think about. But here we go. They use BERT. Okay, I want to know what the transformer decoder is, though. Let's see. Pre-trained. We borrow a pre-trained point encoder. That's not really what we want. Noise-resistant decoder. Okay. I don't actually know. But they probably just trained this transformer here from scratch, just because it's a weird enough data modality that they didn't need to use like a Llama 2, but it'd be cool if they did. Okay. I think that's kind of what I want to talk about there, because now I want to talk about, maybe we can talk about this. This is kind of the kind of noise resistant decoder, which I kind of see as like a kind of a form of data augmentation. So they're basically, it's kind of hard to see, but we can zoom in here, right? So you can see this is the final mesh that they produce, and like, look how good this topology is, right? And you can basically corrupt this mesh. So you can say, okay, here's the same exact object, but with a mesh that's kind of has shitty topology. And then we can effectively go backwards from that and then say, okay, all of these shitty meshes should end up like this, which means that it's a way of making this transformer, autoregressive transformer, this decoder, more resistant to noise, and it produces higher quality topology. The decoder-only transformer may generate low-quality token sequences, and the decoder of the VQ-VAE would typically produce flawed meshes based on these results, on these sequences. In contrast to our noise-resistant decoder, aided by shape conditions, has the ability to resist these low-quality token sequences, producing higher-quality meshes. Right? So they're calling it a token sequence, but it's like basically this, right? So you see how this is kind of being created. It seems like a little bit at a time, right? Each of those little bits is one token in this VQ VAE shape vocabulary. Okay. Now let's go to what I think is the coolest paper here, because this paper kind of ties it all together. And this is JPEG-LM. Okay, autoregressive LLM architectures, that's just a transformer that consumes its own output to produce an output, right? So it's reading all the tokens, and then it generates a next token, and then it takes that next token, combines it with all the previous tokens, and then generates the next token. So it just means a transformer that's kind of pooping out tokens one at a time, right? So in order to do this, you're going to need to discretize, right? You need to take whatever sequence of things, it needs to be things, it needs to be discrete little things that you're outputting. So what are these little things that you're outputting? In this case, the little things that you're outputting are the mesh tokens that are coming from this VQ VAE, right? But in this paper, they do something even more crazy, which is they use canonical codec representation. So they directly model images and videos as compressed files saved on a computer via canonical codecs. Okay, so what the fuck do they mean by a canonical codec? So if I open up here, I'm on my Windows computer. I'm not actually a Windows user. I just use it for streams, but I'm a Linux user. Please don't judge me. If I go in here and I have this random image here, right? So I have some random image here. Here's the image. Okay, cool. PNG image. What if I open this with Notepad? This is what the computer actually sees, right? So like to the computer, this is the image, right? It's just a bunch of weird text that like as a human, I have no idea what the fuck this is, right? It's just a bunch of fucking tokens of weird crap, right? What this paper is fundamentally doing is it's generating images by generating that, right? So rather than generating the images in pixel space or generating the images in some kind of latent space of shapes, it's literally generating images by generating the actual text that represents that image when the image is encoded with something like JPEG or AVC H264. Right, so JPEG is a encoding format for images. So here, this is a nice little blog post that I recommend called Unraveling the JPEG, and it basically goes into like all the different techniques that are used to encode JPEGs or encode images into JPEGs, right? And the whole point of these encoding formats is that they're more efficient, right? So like rather than storing the RGB value for every single one of these pixels, you're creating this what looks like effectively weird garbage, right? That represents that image, and this weird garbage is less memory than the actual image itself, right? And in this one, it's kind of interesting because he's like messing with the different things in here, and you can see how like they're encoding for different concepts inside this image. Right, so it's not like if you mess with one of these, you're only going to change one pixel. If you mess with one of these, like it's almost completely corrupted. It's like it needs to be in this exact little format. And that means that this is actually a very difficult task, right? Because it's not like the language model that generates this can kind of half-ass it, right? If it's going to be generating it, it needs to be perfect, right? So you're taking your image or your video, you're compressing it into this sequence of weird tokens, and then the language model is literally generating the sequence of weird tokens, and now you just have the image. And it actually kind of works pretty well. Like, obviously, this is the early days. You know, it's not like we're comparing this to the Flux or any of these, like, super next-level image generators, but the fact that you can even fucking do this is pretty amazing, right? That you can generate images basically just by generating the encoded, compressed version of them token by token with a language model. Okay. And I did want to show this as well. So there's a lot of these different codecs, right? JPEG is pretty standard for images, but then within, for example, video frames, you have different ones here. So you have MJPEG versus H264. And they have different, it's not like there's one that's the best, right? So different codecs have different advantages. So for example here, H.264 is going to be lower quality, which means it's losing more information, right? So whenever you're streaming something from Netflix, if it's using H.264, it's going to be lower quality than MJPEG, but it's more efficient, which means that there's less information to send. Maybe the decoding speed is better, right? Because every single frame that you receive from Netflix needs to be decoded such that you can actually turn it into an image that you can display on your computer, right? So if the decoding speed is very slow, that's probably going to be kind of annoying, right? So you want something that doesn't lose too much information, and also something that can be encoded and decoded relatively quickly. And there's all kinds of little tricks here. For example, in H.264, usually you're passing in frames, these iframes that are further apart in time, and then the subsequent frames are basically just, you're not encoding the entire image, you're just encoding the difference between this P frame and the I frame, right? So that's a lot more efficient than sending every single frame, is that you send every fifth frame, and then the other frames you're just saying, okay, well, here's the difference between frame number 5 and frame number 1. That difference is going to be a lot cheaper to encode than the entire frame number 5. Okay, and in this case, right, they're literally generating these with a language model. We pre-trained JPEG-LM from scratch, although it would have been cool to see if pre-training from scratch is better than just using a pre-trained model, right? Like, imagine if you get some transfer from just generic language model pre-training into this absurdly specific task of generating encoded images. The other reason I think this paper is cool, specifically for today's discussion, is that they actually compare this directly to VQ-VAE. So they try both things, right? They try kind of what these guys did here, right? Where they say, okay, we're going to train a VQ-VAE. This VQ-VAE is going to effectively learn this vocabulary of shapes, right? And then our language model, we're going to train it to output tokens in this shape vocabulary. They do a similar thing here. They're like, okay, well, what if we train a VQ-VAE to turn images into tokens in this kind of like 2D image space, and we're going to compare that to just literally outputting the individual tokens that compose a compressed JPEG on your computer, right? So the vocabulary here is just 256 discrete values and some special beginning of sequence and end of sequence tokens. Given an image X, we propose some model, right? You have your model P here. Your model P is producing the JPEG token. So you're taking your image X, you turn it into a JPEG. That is some sequence of tokens. You're trying to output that sequence of tokens given the tokens up until that point, right? So you're basically given all the tokens up until this point, all the little things that you see, right? These things here, this crap here, you're giving it basically up until here, and then you're asking it to predict the rest of it. And that's what's going on here. Right? So it's predicting the rest of that given the input. Autoregressively, it's just a language model. They use conventional LLM architectures without any vision-specific modifications, no convolutions, no 2D positional embeddings to maximize the model's generality. So they were trying to make a point here, right? They're trying to make a point that you have a lot of image-specific biases that you're putting into these things, right? So for example, here, whenever they're using this VQ-VAE, it probably has a convnet, right? It maybe has some notion of position embeddings. You maybe have some notion of position embeddings in this transformer, right? You're putting in all these little tricks, right? All these little biases that make it easier for the model to learn the task because you're using your human intuition to say, hey, if I give it a little positional information in the form of a position embedding, it's going to have an easier time learning, and it does. But in this one, they kind of wanted to prove a point, and they're like, hey, we didn't add any of that. No position embeddings, no convnets, right? No special architectures that are basically baking in some kind of bias into this. It's just literally a language model that outputs codec. Okay. We pre-trained a 7B Llama 2 model from scratch using 23 million 256 by 256 images. JPEG encodes each image with a quality factor of 25. So JPEG encoding, you can there's a slider on how lossy do you want it to be. We first used the 10K images to derive 320 PPE tokens as our vocabulary entries. And each image in our training data leads to 5K tokens. So they're basically turning an image into about 5K tokens. The 7B Llama 2 pre-trained from scratch. They do video as well, but it's really just 15 frames. So it's kind of like a tiny little video. And I think, let's look at this. So this is kind of really showing you exactly the difference between, for example, compression, right? So the VQ-VAE, this thing here, is lossy, right? It's losing information. When you take this image, this high dimensional image, and turn it into this lower dimensional feature, you're losing information there, right? So whenever you reconstruct it, it's never going to be perfect, right? You're never going to like perfectly reconstruct the image because you lost information when you went from here to here, right? The same thing is happening with a JPEG, right? Whenever you take your JPEG and you go from the actual image into this encoded JPEG representation, and then go back to the image, you're going to lose information, right? Because this is less memory than this, right? You're losing information there. So here, they want to show you how the information that you lose is actually different, right? So if you take this original image of this guy standing here in front of this coffee shop or whatever the fuck this is, if you take that image, feed it through the VQ-VAE, and then it gets compressed, and then you decode it back, you can see how it lost information, right? But the information that it lost is kind of like agnostic to that type of information, right? So if you can see here, like it actually did the background better than the JPEG encoding. So if you see here, this yellow line here and this yellow line here, I feel like that is a better, or there's less information lost between the background here and the background here. But look at the face. Look at how much worse the face is, right? So the vector quantization, this is losing a lot more information in the face versus JPEG, right? Because JPEG encoding is something that has been designed by hand, right? And all of these encodings, usually they have all kinds of weird little tricks where like the faces are better, like parts that are in the center of the image, right? Like stuff that is repeated, like the background. So if you have a lot of the same color, that kind of gets encoded in a more lossy way versus if you have things that are very different from the background, right? There's all these little handcrafted human tricks. And because of that, you can see here that the JPEG encoding actually, it might not get the background as well as the VQ, but it's doing the face a lot better, right? So the whatever compressed version of the image you're getting with this JPEG, the JPEG is significantly better in detailed but highly perceptible elements like small human faces and text characters. VQ has a relative advantage in color and sharpness preservation. Okay, so even though they're both lossy compression methods, the JPEG one is a little bit better, which makes me think that imagine this paper here, but rather than using an LLM to generate these VQ tokens effectively, right, the little shape tokens, you're almost directly generating a mesh file, right? So take the stuff that they're doing in this paper where they're literally directly generating the compressed JPEG. You could do the same thing with a 3D file format, right? Like a STL file. Like what happens if you have an LLM that directly outputs an STL file, basically like token by token, like byte by byte, right? Pretty cool. Let's zoom out. Okay. We were already looking at that. The Llama 2, which we saw. They're evaluating this on ImageNet, which is fine. You know, this is unique enough and cool enough and has enough novelty that, you know, the fact that it's just on ImageNet and it's a relatively small model is totally fine. JPEG-LM consistently outperforms the VQ transformer. Conclusion, we generate images and videos using mainstream LLM architectures, autoregressive transformers, with a canonical codec representations JPEG for images and AVC H264 for videos. This work is effectively unifying the paradigm of language generation and visual generation. An approach almost void of prior work, likely because there are many potential assumed challenges with the method, right? Like, that's why this paper is cool, is because nobody really tried to fucking do this, because it's almost like a stupid idea. It's like a stupid idea that works, right? And that's why this paper is so cool. Our models also do not use any vision-specific modules like convolutions or 2D positional embedding. So it's not like the transformer has all this fucking structure baked in. Because, for example, this is how a lot of vision language models work right now, right? They're using these vision transformers, which are using kind of like a ConvNet bias here, right? Where they're basically like taking an image, they're turning it into these patches, and then they're feeding each of these patches with a position embedding into the transformer. So whenever you have something like the Llama Chameleon, right, which is generating images and text arbitrarily, interleaved images and text, is generating these visual tokens, and then those visual tokens are then being decoded into an actual image, right? So you're still relying on something that is encoding that image into some image representation, and then something that can then take that those image tokens and turn it back into an image, right? Which is kind of what they're doing here, right? In this paper, they're relying on this VQ-VAE that takes the 3D object, turns it into this sequence of shape tokens, then the transformer generates more shape tokens, and then they can take those shape tokens and turn it back into a mesh, right? In this case, you don't need to do any of that, right? You don't need to be doing any of this encoding and decoding. You're just literally going into JPEG, right? The JPEG is the encoder, right? The STL is the encoder, which is pretty cool. All right. Yeah, I mean, the results are not like amazing, but it's like a tiny ass little model on a kind of tiny little data set. It's really just a proof of concept. And I think it's really, to me, it's all about like what doors does this open? Because there's so much there, right? It basically means that we can just generate things directly by just generating the actual representation of that thing in a computer, rather than coming up with some fancy representation that is effectively hard-coded for some specific 3D thing or 2D thing, and then using that. I don't know. Maybe I'm trying to. Maybe there's not as much between these papers as I'm kind of making it seem. But to me, these three papers together have kind of changed my view about where we go in the future, right? Because here you have your standard kind of like overly complicated like reconstruction pipeline. I do like the fact that they're going into normal images. They're using normal images here. They're using the fact that these pre-trained diffusion models can generate normal maps in order to generate additional signal to train this effectively UNet that creates SDFs with little, basically this is like almost like a little nerf here, right? Like a little nerf that outputs the color, little nerf that outputs the normal, and then you can use marching cubes to get the actual final mesh. Here they're taking it one step further, saying, okay, well, fuck the explicit 3D representation, or fuck the nerf and the Gaussian splats. We're just going to output these things directly token by token using an autoregressive LLM. And we just have to do something fancy here with a VQ-VAE so that we can basically discretize a mesh into a sequence of shape tokens. And then here, they're going like just full retard, right? They're saying, okay, we're not even going to use a VQ-VAE to come up with some fancy token vocabulary that we can then train a LLM to generate. We're literally just going to train the LLM to generate a JPEG in text form. And it somehow works. Pretty cool stuff. All right. I feel like today's a sleepy stream. Maybe it's a little bit too technical. I don't know. I feel like maybe I went a little bit too deep. You know, maybe people don't care as much about the nuances of 3D representations and generating with transformers, but I thought it was pretty cool. So that's pretty much it, guys. That's all I got. Let me see if there's any other interesting pictures that I had ready for you guys. We have the triplanes, SDFs. We have the depth anything. Had the normal maps. We had this nice blog post on encoding, JPEG encoding, right? There's a lot of like pretty cool stuff that people have come up with over the years to efficiently encode images, right? Like, look at this. H.264 versus MJPEG. Huffman coding, which is kind of like a more higher level concept here. Optimal prefix code that is commonly used for lossless data compression, so not JPEG, right? PNG is lossless. Here you have marching cubes. Nice. How do you get a mesh from a SDF? Topology. And then here, just the GIF of the MeshAnything, which I think is really cool. This topology is so good. Like, the topology here is so clean. All right. OpenUSD generator on the way. USD is the universal scene description, right? Universal scene description. Yeah. So rather than generating a bunch of different 3D assets and then putting them all into some scene inside Blender or Unity or something like that, you literally just output the entire file, right? So that could work. You know, that's a good idea. Like, honestly, SHZ, I think that's a pretty good idea. Like, because I think part of what makes this even more promising is that this isn't even, like, even though these results are kind of shitty, like, for the amount of compute that they put into this and the data sets that they use, this is very impressive, right? If they were using, like, a huge llama model, like the llama 401, 405B or whatever the huge one is, and they were training it on, like, billions of images, like, okay, this paper wouldn't be that impressive. But the fact that it's just a 7B Llama 2 with 23 million images from scratch, and you can get this, that's pretty impressive. I really like Rodin services, but I can't wait for high-fidelity open-source 3D AI generators. There's a bunch of open-source 3D AI generators. They're just not, like, super great, you know? What is Rodin services? Rodin services. This? It's like a denture? The fuck are you talking about? Rodin Legal Services? The Rodin Museum of Art? Auguste Rodin, French sculptor of sumptuous bronze and marble figures. Sumptuous? What? Okay. Let me just summarize this. I don't know what else to add, so I think I'm just going to summarize this, end it, but... All right. So today's stream was called MeshFormer versus MeshAnything, and it started off with just kind of a comparison between these two different ways of generating meshes. So we have a paper called MeshFormer and a paper called MeshAnything. And MeshFormer is, I think, representative of kind of your bleeding edge multi-view reconstruction papers. You know, we've read a bunch of these at this point, where basically what they're doing is they're using multiple RGB images in order to create a representation of the object, and then using that representation of the object to generate a mesh with something like marching cubes, right? So kind of relatively standard. I think what kind of sets this one apart is the quality. So the quality of these meshes is pretty good. And the other thing that sets this one apart is the fact that they have these normal maps, which are being created by a diffusion model that has been trained on real images, which is a pretty cool idea. I think there's other papers that also do this. They have the depth maps, which can be generated from these diffusion models. So that's this paper. And then we compared it to this paper here, MeshAnything, because they're doing something fundamentally different, right? They're generating a mesh using a language model token by token. And in order to have a discrete tokens that they can generate, they use a VQ VAE, which is kind of an older concept, but it pops up time and time again, in order to create these kind of shape tokens, right? And then those shape tokens can then be generated by the transformer. And then once you have that sequence of shape tokens, you can just use the other half of the VQ VAE to decode it into a full mesh, right? So because you're decoding this token by token, you get some stuff for free, right? You get this kind of free lunch of being able to fuck around with the order of the tokens, right? These low quality token sequences where you're purposefully kind of injecting noise and then using that to basically get a decoder, right? This part here that is robust to the order of those tokens, which means that it can generate good topology even if the sequence of tokens is low quality, right? So cool concept, and the fact that you can get good topology maybe means that meshes are going to have a comeback, right? Because if you can generate very high quality meshes with good topology, that's pretty useful, right? Because it means you can very easily start using it in any of the current 3D industry pipelines. Animation pipelines, rendering pipelines, any of these Unreal Engine, Unity, like these types of programs that rely on meshes as the standard canonical 3D representation. So that was the comparison between MeshAnything and MeshFormer. And then I thought that I wanted to kind of throw in one extra paper here that was related because it kind of takes this one step further, right? And rather than having all this complicated stuff here, and then this one here simplifying it by using a language model that just outputs tokens, this one takes it one step further. And in this paper by Meta, they generate images and videos by directly modeling images and videos as compressed files saved on a computer via a canonical codec such as JPEG. So they pre-train a language model on JPEG images that directly outputs a JPEG token by token and actually creates an image, which is pretty insane that it can do that, right? It's like you're taking this image, and if we open this with Notepad, right, it's like the language model is literally generating that. Which is crazy. And they did a nice little ablation study here and showed you that the JPEG encoding is actually probably better than the VQ VAE encoding. But it's not 100% true because, I'm sure if you had trained a better VQ VAE, like with more images, at some point you would probably surpass the quality of the JPEG, but I don't know. I haven't done the experiment, so I don't know for sure, but quite impressive. That's pretty much it, guys. Happy face, and then I don't know this emoji. What is this emoji? It's like a little dancing heart hugging face thing. IDK Snooks. People may be still getting used to the join in for the new stream time. Yeah, I mean, I'm not too concerned, I'm doing these almost more for myself, I just love learning and then sharing what I've learned. But if people find value in it, that's great. If people don't find value in it, I'm okay just kind of learning and sharing. That's pretty much it, guys. Thank you, Snooks. Thank you, whatever little dog face. SHZ87GN. They call me Ken. Sotaki. Numa Nibuni. Oma Viva, Miguel, Kong. Thanks, everybody. And I think this guy's trying to... I've posted the link to Rodin by Hyperhuman, automatically filtered out. They have a model coming Q4. Rodin by Hyperhuman. Okay, we're going to... Rodin by Hyperhuman. This guy's trying to, push some bullshit here. Okay, do you work for these guys? Here's the problem. Like, the problem with these is that it's like, these are cherry picked, right? Like, this is I ran into this problem with, I think it was like Meshy or something like that. I tried a couple other mesh generators and like all of them were way worse than advertised. So I don't like really trust this. Let's see. Text input. Hyperhuman. I'm not going to sign in, dude. Just do it for free. Mark Zuckerberg. What the fuck is this weird incision on his like neck? What is that? Does Mark Zuckerberg have that? Does he have like some fucking weird like thing on his chin? No, he doesn't. What is that? What the fuck? Do they all have that? Teto Nugan. There's like some politician I don't understand. All right. I don't know. I'm not getting paid by Rodin. Okay. All right, guys. That's it. I'm going to go do some other stuff. Thanks for hanging out. Hopefully you got something out of this. If not, have a great weekend.